It's this invisible force, right? It can silently hold, well, our entire digital lives on a little spinning disk.
Or guide a massive ship across the ocean. It's pretty incredible.
Exactly. We're talking about magnetism, and it's so fundamental, so deeply woven into everything we do that we hardly ever stop and ask, how does that pull actually work?
It's just there.
Yeah. So today, we're taking the ultimate shortcut. We're going deep into the science, the history, the breakthroughs, and frankly, why magnets are just completely indispensable today, our mission. To get a real grip on this hidden power fast.
Okay.
We're diving in. Okay, let's unpack this.
And I think what's really fascinating is how this whole story scales up. You go from someone finding a weird rock
Right?
to understanding forces happening inside an atom, and then using that knowledge to understand, well, our entire planet. It's quite a journey.
Okay, let's start really small. Atomic level. Where does this force actually come from? It's not like there's a battery inside a magnet, right?
No, not at all. It all boils down to electricity, fundamentally. Specifically, the movement of electric charges right inside every single atom.
Movement. Like electrons orbiting the nucleus.
That's part of it, yes. Electrons orbiting a nucleus definitely create a tiny magnetic field. But there's another motion, and for the magnets we stick on our fridge, this one's arguably more important.
Okay.
It's the electron spin. They're not just orbiting, they're also spinning on their own axis. Think of it like the Earth orbiting the sun, but also spinning to give us day and night.
Ah, right. So that spin also creates a magnetic field.
Exactly. Any moving electric charge generates a magnetic field. So you've got these two tiny fields from orbiting and spinning for each electron.
Okay, but hang on. If every atom in, say, this wooden desk has electrons spinning and orbiting, why isn't the desk magnetic? Why can I stick a paper clip to a fridge magnet, but not the desk?
Good question. It comes down to organization, or, well, the lack of organization in most things. In your wooden desk or plastic or aluminum, those tiny atomic magnetic fields are all pointing in random directions.
So they just cancel out.
Perfectly. They all cancel each other out. The net effect is zero. No overall magnetism. But then you have special materials.
Like iron.
Exactly. Iron, cobalt, nickel. These are the main ones we call ferromagnetic materials. Something different happens inside them.
And that difference is the structure.
It's about structure, yeah. These materials have regions inside them called magnetic domains. Think of a domain as like a tiny neighborhood where all the atoms have decided to cooperate.
Cooperate how?
All their individual atomic magnetic fields. Those little fields from electron spin mainly line up perfectly, all pointing the same way within that domain.
Okay, so tiny aligned teams. But if you just pick up a normal piece of iron, it's not usually a magnet yet, right?
Right, because in an unmagnetized piece of iron, the domains themselves are pointing randomly. So you have organized teams, but the teams are all facing different directions. They still cancel out overall.
Ah, okay. So making it a magnet means getting the domains to line up, like pointing all the teams in the same direction.
Precisely. You introduce a strong external magnetic field, or sometimes even just stroking it consistently in one direction can do it. You're essentially telling all those domains, okay, everyone, face this way.
And once they're mostly aligned, boom.
Magnet.
Boom. Magnet. You get that strong overall magnetic effect, and that's when you get the distinct north and south poles, the classic poles, and the basic rule. Opposites attract, likes repel, non-negotiable. North attracts south, north repels north, south repels south, always.
And this force operates within an area around the magnetic field.
Yeah.
How do we visualize that?
Yeah, the field is the region where the force acts. The standard way to picture it, the convention, is to imagine invisible lines coming out of the North Pole,
Okay.
looping around through space and going back into the South Pole. You can actually see this pattern if you sprinkle iron filings around a magnet.
Right. I remember doing that in school. It maps it out.
It does. And understanding that field, that flow from north to south, is really the key to harnessing magnetism for technology. Okay, so mapping that field, even knowing about the pole, that started way before electrons or domains, right? This history goes back thousands of years. To a rock, you said.
Yeah, it all starts with lodestone. It's a naturally occurring, already magnetized form of a mineral called magnetite. Just a rock you could literally find on the ground that would attract bits of iron.
Wow. And who first noticed this?
Well, the earliest written records we have connecting it to sort of philosophical thought come from the Greeks. Thales of Miletus, around 600 BCE, documented its strange attractive properties.
So the Greeks knew about the attraction. But just knowing it's weird is one thing. Actually using it is another.
Absolutely. And this is where ancient Chinese civilizations made a huge leap. While the Greeks were pondering it, the Chinese figured out you could use lodestone.
To find direction.
Exactly. They created the first compasses,
Yeah.
taking this weird rock and realizing it would consistently align itself with the Earth's north and south. That was revolutionary. It completely changed navigation, exploration, the world, really.
Okay, here's where it gets really interesting for me. You've got this tool, the compass, based on a mysterious rock guiding ships. That sets the stage for a massive conceptual jump, doesn't it?
It does. Fast forward quite a bit to the year 1600. We meet an English physician, William Gilbert. He's the one who really started to turn this from, let's say, observation and practical use into actual science.
How so?
He published this landmark book, De Magnete, which means on the magnet. And its central idea wasn't just about how magnets work or how compasses work. It was much bigger.
What did he propose?
Gilbert proposed that the Earth itself, the entire planet, is one giant magnet.
Oh, okay, hold on. Based on what? A compass needle pointing north?
Essentially, yes. He made meticulous observations using spherical lodestones, little model Earths, and compasses. He argued that the only way a compass needle consistently points north no matter where you are on Earth is if the planet itself had its own magnetic poles.
That is a huge leap. Thinking of the Earth as a giant version of this weird rock, that's foundational.
Absolutely. It laid the groundwork for understanding terrestrial magnetism. But there was still a missing piece for the modern world. If Gilbert linked magnetism to the planet, the technological explosion needed one more connection.
Electricity.
Electricity. For a long time, people saw electricity, static shocks, lightning, and magnetism as separate things, maybe related but distinct forces.
Okay.
The game changer came in the 19th century with scientists like Hans Christian Ørsted and Michael Faraday. Ørsted discovered, almost by accident, that an electric current running through a wire could deflect a compass needle.
Meaning electricity creates magnetism. And then Faraday brilliantly showed the reverse. If you move a magnet near a wire or change the magnetic field around it, you can generate an electric current in the wire. Magnetism creates electricity.
They're two sides of the same coin. Electromagnetism, that discovery that you can swap between electricity and magnetism using motion, that's the key.
That connection unlocks basically everything. Motors, generators, modern tech.
Pretty much everything electrical we rely on hinges on that fundamental link. So yeah, we connect this to the bigger picture. Understanding electromagnetism just threw the doors wide open. It meant magnets weren't just navigational tools or curiosities anymore. They became truly indispensable tools for building modern civilization.
Right. It's easy to just list things off: motors, hard drives, MRIs, but maybe we should touch on why magnets are so perfect for these jobs. What makes them better than, say, using just electricity or mechanics?
Okay, good point. Let's take electric motors and generators. You need to turn electrical energy into motion, or motion into electrical energy.
Like in a power plant or an electric car.
Exactly. Magnetism provides this incredibly efficient way to do that conversion. The push and pull between magnetic fields and electric currents lets you create rotation from electricity, or electricity from rotation, with relatively little energy loss. There's really no other practical way to do it on a large scale.
Okay, that makes sense for motion. What about storing information? Like hard drives. We store tons of data using magnets. Why not just use electrical charges?
Stability. Permanence. Think back to those magnetic domains we talked about.
The little aligned neighborhoods inside the iron.
Yeah. Once you align those domains in a tiny spot on a hard drive platter to represent a 1 or a 0, they stay aligned, even when you turn the power off.
Ah, non-volatile memory.
Exactly. Electrical storage, like RAM in your computer, needs constant power to maintain the state. Magnetism lets you store data reliably for years without power. It's durable, dense storage built on that atomic-level organization.
And then there's the really high-tech stuff, like medical imaging,
Yeah.
MRI machines.
Right, magnetic resonance imaging. This is just incredible. They use these immensely powerful superconducting magnets, way, way stronger than your fridge magnet, to do something remarkable.
What's happening inside the tube?
Essentially, the strong magnetic field forces the protons, mostly in the water molecules within your body's tissues, to all align in a specific way.
Oh.
Then, a radio frequency pulse knocks them out of alignment. When the pulse stops, the protons snap back into alignment with the magnetic field, and as they do, they release a faint radio signal.
And the machine detects that signal.
Detects those signals, yeah. And because different tissues have different amounts of water and relax at slightly different rates, a computer can analyze those signals and build up this incredibly detailed picture. Cross-sections of your brain, your organs, soft tissues.
And the key advantage over, say, an X-ray.
No harmful radiation. X-rays use ionizing radiation, which can damage cells. MRI uses magnetic fields and radio waves, which are non-ionizing. It lets us see inside the body with amazing clarity without that risk. It's a huge benefit, especially for repeated scans.
It really is amazing. From electron spin, this tiny quantum property scaled up to map inside a human body safely. It seems like magnetism is this ultimate super versatile tool, powering speakers, keeping food cold, running factories, storing our memories.
It underpins so much of modern life, often completely invisibly. Hashtag tag outro. So if we connect this all back to the bigger picture, you really see this incredible thread, don't you? From the almost unimaginably small, the spin of an electron creating a tiny field, to organizing those fields into domains for data storage, all the way up to generating massive power or using planetary scale fields for navigation. It's quite the range.
So what does this all mean for you listening right now? We started way back with Thales finding a weird rock.
And we got to William Gilbert's huge idea.
Yeah.
We live on a giant magnet. And that realization, that planetary scale, has implications way beyond just making a compass work or, designing the next hard drive.
Absolutely. Gilbert put his finger on something vital for our actual existence. Think about this. Deep inside the Earth, there's this churning, molten outer core, mostly iron and nickel. It's incredibly hot, and it's moving, a giant flowing conductor.
Right, and that movement of conductive metal deep within the planet acts like a colossal dynamo. It generates the Earth's magnetic field, the magnetosphere, which stretches far out into space.
It's enormous.
And this field does way more than point north. It acts as a shield. Planetary force field, really.
Protecting us. Yeah, protecting us from the constant stream of charged particles boiling off the sun, the solar wind, without the magnetosphere deflecting most of that damaging radiation.
Our atmosphere would likely be stripped away over time. The surface would be bombarded. Life as we know it probably couldn't exist here.
So this force, born from tiny electron spins, scaled up by planetary motion, isn't just useful for technology, it's fundamental to our survival. An invisible shield powered by the heart of our world. Now that's something worth thinking more about.